I'm going to report on joint work with Isabelle Gallagher, Laure Saint-Rémy, and Sergio Simonella. In fact, it's a series of work, but the main focus of the talk will be on the fluctuating Boltzmann equation. So let me just give you an outline of the talk. So we're going to model hard sphere dynamics, basically just a kind of billiard with balls bouncing into each other. And what we're interested in is the fluctuation of this system. First, out of equilibrium for short time, and at equilibrium we can reach a much longer time scale. And at the end, I'll give you some idea of the proof at equilibrium. Of the system at equilibrium. So let me start with the model. We consider a box of size unit size 1. It's periodic for simplicity, and in this box you imagine you have a billiard of n balls, so n is large, and the balls they move in straight line until they collide with each other, elastic collision. It's basically a Newton law for this dynamics. So the dimension will be always larger or equal to 2. And the important feature in this system is the size of the ball, epsilon, which has to be small because the n balls have to fit into this box. And I will tell you how this epsilon is tuned with the n balls. I'm going to use this notation throughout the talk. So each ball has a position xi and velocity vi at time t, and the collection of the n balls is zn with all the. Okay, so the important point is that the n and the epsilon are linked into a so-called dilute limit scaling, and sometimes called the Boltzmann grad scaling, such that n epsilon d minus 1 is equal to 1. If you've never seen that before, you may wonder why, and in particular, usually you want to remove this minus 1 and it would be more practical, but I mean, it would be a denser gas. But here, the idea is the following. We consider a very dilute limit, and each particle will, on average, have one collision per unit time. And one collision per unit time means that a particle, let's say this one, per unit time is going to move in straight line. So it's going, if it has velocity 1, say, it's going to cover a very thin tube of length 1 and of surface here area epsilon d minus 1 because of the size of the ball. And you have, imagine you have n particle uniformly in this box. Then you want one collision roughly per unit time, meaning that this is a good balance, that one of the n particle will be in this, on average, will be in this tube. So this is the reason of the Boltzmann grad scaling. Of course, some particle will never collide, and other may collide a huge amount of time. It's one has to think of an extremely dilute gas. And we're always going now to consider a limit of n large and epsilon go to 0 simultaneously. So we'll always be linked by this relation. So as I said, the dynamics is the one of billiard. When two balls, the balls basically move in straight line. So xi, the derivative is vi. Nothing happens until they meet. Once they touch, you have a specular reflection, they immediately change their velocity according, I mean, write the relation. The important point is that the momentum is preserved and energy is preserved. But it's really like a billiard ball. Two important features I want to stress of this dynamics. One is that the Newtonian dynamics is reversible. So if you start from one configuration, let the motion go on for a long time, or short time, whatever, then you stop, you reverse all the velocities, everybody is going to come back in the initial position. There's absolutely no loss of memory, everything is encoded, it's deterministic, everything is encoded in the dynamics. The other important issue for what we're going to say is that the dynamics is unstable. Okay, I won't make it formal, but what do I mean by this? So imagine you have two particles which are about to collide, like here. In this case, if you shift one of the particles, say the one below, by epsilon, which is nothing, then they're going to avoid each other maybe, and you don't have collision. So a tiny shift of one particle, certain collision may not happen, other collision will happen, and you'll see a priori, at least microscopically, a completely different history. However, it's still deterministic depending on your initial data. This is the history you're going to see and remember forever. So what do we want to do? We don't really want to describe the detailed feature of the dynamics. We just want a statistical description. So let's say at time 0, all the particles are, all the atoms of the fluid are within in the center of the box. They're described by some statistical average. So that will be the density of these n particles. And we want to know what is they're going to spread into the dynamic. We want to know what is the distribution at a later time t. So this obeys Whewell equation, which here looks pretty nice in the sense that there is only the transport part, and all the difficulty is collision, because to that you have to add boundary condition. When two particles meet, then they bounce, and the whole equation becomes then a nightmare to study. Okay, so the only source in this system, the only source of randomness is in the initial data. So just to have a clear framework in mind, let's imagine that all the particles initially are independent. In this case, you choose a product measure as an initial data, and each particle starts according to some initial distribution with velocity and position prescribed according to F0. So we can't really do that exactly as a product measure. We need to tweak a little bit the measure, because the particles are hard sphere, they're not allowed to overlap, and there's always some exclusion condition in the measure, in the initial measure, but it's not such a big deal. It's easier to present with a fixed number of particles, the canonical picture. However, for us, we're going to use the ground canonical formalism when the n is actually a random variable. And what we're going to fix is more the mean of the number of particles. So we do epsilon, but we just want the same condition, that the mean the number of particles is again related to the epsilon, and they both will be tuned in this way throughout the talk. So sometimes I talk about n, sometimes I talk about mu, but the results are obtained actually in the ground canonical formalism. First step, level 0 of the theory, is to describe what's going on for one particle, typically how the gas is evolving, and this one way to see that is to look at the marginal for one particle. So this marginal depends on epsilon, and Z1 will be particle 1. They are all symmetrical, they're all exchangeable, so it doesn't really matter whether I follow particle 1 or any other. And later on, we might use K particles, in which case this is the K marginal of the first K particle. So these are for the notation. Now let me just briefly summarize probably 40 years of theory within one theorem. If you choose this type of initial data product I mentioned before, with F0 smooth density and properly bounded away from zero, then there exists a time t such that the first marginal F1 converges to the solution of the Boltzmann equation, which Boltzmann equation is written here. For those who are not familiar with Boltzmann equation, it's not so useful to retain the precise structure. It was just to say that there is some limiting equation, and the first marginal is actually converging to the solution of this Boltzmann equation, starting from the initial data F0. So somehow the Boltzmann equation describes the typical behavior of the system. Convergence is again always understood in this limit, low density limit, when the size of particles, number of particles are scaled in this way. And notice that there is a lot of work I will give some references, trying to get also a quantitative result for this convergence.
Sorry, can you remind me again what F1 of epsilon is?
Yes. So F1 is the first. Yes, here it is. F1 is the first marginal. Okay, of for so distribution, typical distribution of one particle. And so this theorem says that typically a typical particle follows Boltzmann equation. Its density follows Boltzmann equation. And before I'll give you some overview of the literature, I just want to stress a few facts about this convergence. So on the one hand, this F1 is the distribution of a typical particle for fixed epsilon, so it describes the microscopic dynamics, this Newtonian dynamics. On the other hand, Boltzmann solution is at the mesoscopic level, and they're related within some limit. However, there are important features which are not shared by these two functions. On the one hand, the deterministic description follows from this Hamiltonian dynamics, so it's completely reversible. And on the other hand, Boltzmann solution is actually a solution of some dissipative equation. It has some irreversibility encoded into the limiting equation. So, as such, it's not a problem, but there has been many discussion about this fact, and I want and how somehow a dissipative equation could be a good description of a system which actually never loses any memory. But it's a description only at the level of projection on the typical density. And actually the point of the talk is to get further detail on this difference between the two quantity. So this theorem has a very long history, and actually I haven't quoted all the researchers contributed to establish this convergence. It started with the breakthrough work by Lanford, and then there has been really a huge effort to go beyond for example, the hard sphere setting to have smooth potential, to also more recently to have quantitative convergence. So this, in particular, the how fast this gamma epsilon goes to zero, and so there are here some people in the audience, including Chiara. And Isabelle Gallagher, alors Saint-Raymond, Benjamin Texier have been doing some contribution, and Mario Pugliarenti, Chiara, and Sergio others. Denlinger has been also had important contribution on this quantitative side. Okay. So now we have more or less. I tried to summarize this convergence of the first marginal. Another point of view about this is to say, okay, I mean, this first marginal actually of the density, I can view it, it's equivalent to say that it converges and more or less that you have a convergence of the empirical measure. So empirical measure, you choose the test function h, depending on x and v, and position and velocity. You average this test function over all the n particles, and you look at the distance between what should be the mean, namely the solution of the Boltzmann equation against this test function. And what the previous theorem implies is that this goes to 0 when epsilon goes to 0. So I want to do one computation to see, I mean, how, from what it follows. It's actually a little bit more than the previous theorem. So when you have a square like that, you don't have much choice, so you just expand it. And once you expand, you have two types of terms. First type is when you have twice the diagonal term. You have the same I, and this is a contribution of order n. You have n terms on the diagonal. It gives you this first term, and there's always n squared due to this 1 over n. And then you have the cross contribution, I mean the two contribution. You choose one I and one j and put them together. Sorry, it's a bit painful computation, but it will be important for the following. The non-diagonal term, you have n times n minus 1 term, so they balance with the n squared. So the first term is okay because it's of order 1 over n, so the first term goes to 0. The second term, it's less clear because this is of order 1, but you can rewrite this thing in terms of the two-point correlation function. So now the density of Z1, Z2 of two particles, and you compare it with the limit here, which should be a product. And that is known as propagation of chaos, that the two-point correlation function, which is here, somehow factorizes in the limit. The particles are essentially independent, and in this case, the density becomes twice the density of a single particle, which is this product, and it goes to 0. So this chaos property is actually also one thing derived in the theorem I mentioned before. I haven't developed that, but as a consequence, you see that the empirical measure, here it's only tested against one test function, converges somehow to the measure given by the solution of the Boltzmann equation. So this can be in this way, in terms of empirical measure. You want to interpret this theorem as a law of large number. So you have a particle system, you have a limiting mean, and once you average, you concentrate to a solution of the Boltzmann equation. So you imagine you start from some f0, you know roughly where the mean is going to be. It's going to follow this ft. And the next step we want to do is, okay, we started from a particle system, so now it's not exactly equal to the density f0. There are, of course, a tiny fluctuation, if I zoom in at the right scale, close to around f0. And the question is how these fluctuations are going to evolve in time. And this, in probabilities, the next level is central limit theorem. So large number, central limit theorem. So let's, and so what is I mean, this is the standard. This is the standard rescaling. Instead of dividing by 1 over n, now next step you divide by 1 over square root of n, and you remove the mean from the, you center your variable, and you want to describe this new object now. So zeta somehow, zeta of epsilon, you should see as a kind of recentered and rescaled empirical measure. It's called the fluctuation field. You test against test function h, and you want to describe this time evolution. So to give you a better feeling now of this rescaling, I want to redo the same computation as before. Namely, now, before I was computing the empirical measure against this limit, and now I will do the same thing, but for the new rescaled test function. So instead of dividing by 1 over n, I divide by 1 over square root of n. I expand, and again, I have the diagonal term and I have the cross term. So you see now that I don't have 1 over n squared, I have 1 over n because of the rescaling, and so this term becomes of order 1, so it's an important term. And now here I have a problem, because now I have n squared divided by n, so even so, I mean, propagation of chaos tells me that this goes to 0. I have to evaluate properly how it goes to 0, because a priori it's not multiplied by a constant, but it's multiplied by something which diverges. So the decay of the two-point correlation has to be properly evaluated, because we would like to understand it. I will mention quite a lot. There has been some work by Spohn about, I mean, how to quantify the decay, and it turns out that it has some relevance, because for the fluctuation, the correlation matter. So this term, sorry, this term now, which is here, essentially it's a correlation between, let's say, one particle and another, particle 1 and particle 2, multiplied by something of order n. So let's see. I just rewrote it here. So particle 1, particle 2 multiplied by something of order n. I want to take the expectation. So what are the two possibilities? Well, very likely, actually, particle 1 and particle 2 are coming from, when I look at them, they're coming from very different region of the phase space. They never seen each other, they don't know each other, essentially it's product. And actually, this term should be essentially 0, and because particles are independent. Well, however, it may happen that at some point, let's say, they hit each other. It could be something more complicated, like series of collision, but maybe at some point they hit each other. And if we want to evaluate what is the cost of two particles hitting each other, you have to remember my initial explanation of the Boltzmann grad scaling. For this, you have tubes, tiny tubes, and they have to intersect. And when you do the counting for that, you realize that the part of the phase space for this guy and this guy to meet is actually tiny when you start. It's of order epsilon d minus 1. However, in this contribution, and so that's why you have propagation of chaos. However, in this contribution, everything is multiplied by a power and by n. So these tiny contributions are somehow enhanced by the multiplication, and it gives you a non-trivial effect of order 1. So the outcome of this discussion is that, and this was understood by Herbert Spohn a long time ago, that there is some recollision, or I mean, he called it recollision operator. I'm not sure that it was the most appropriate word, but there's certainly a quantity of where the correlation matter between the particles, and this quantity will be part of the variance of our central limit. Okay, so now we have more or less defined the setup. Again, for what we're going to say, I don't want to divide by 1 over square root of n, because I'll consider the grand canonical formalism. So the good definition of the fluctuation field is divided by the mean. At least that's one thing which doesn't fluctuate. Since everything is fluctuating all over the place, it's better to settle this one. Okay. Now the theorem is the following. Let's start again from a distribution which is of the same form as the one I mentioned for the convergence to the Boltzmann equation, essentially product, everything is smooth and fine. Then this fluctuation field zeta converges in low on a time scale, okay, from up to some time t star positive towards a solution of some SPD. I will comment this SPD. The first part is a linearized Boltzmann operator. The second part is a white noise with some structure. And this is the fluctuating Boltzmann equation. So this is known as the fluctuating Boltzmann equation. Let me mention some facts. So first of all, this convergence has been conjectured by Herbert a long time ago. And it turns out that when you look at different dynamics with stochastic interaction, namely Kack's model, for example, I won't explain too much this. In the Kack's model, you have a very similar of structure arising. Even so, Kack's model is a probabilistic description of the model without deterministic dynamics. And also, there's some intermediate description with position and stochastic collision by Fredun Rezarolu, where again, a similar type of dynamics arise. Okay, let me...
Sorry,
yes.
Maybe you said I missed it. So the eta is a white noise or a...
So eta will comment on that. It's not completely white, but it's pretty white. I'll tell you. Okay, maybe one thing I should say, and I've forgotten. So I mentioned that there is a time length t for the convergence to a Boltzmann equation. This t is actually not huge. It's pretty tiny. And this t star is more or less of the same order. So you don't do much better, but you don't do much worse. Maybe it's half of t, maybe.
So if you can also convert the central limit here as a convergence to a Gaussian or a distribution or...
Yes, this is, okay, oops, sorry. This guy, I'll comment on that. This guy is a Gaussian process, indeed. So let me say a few facts on the dynamics. So the first part is a linearized Boltzmann operator, so around the solution Ft. So how to understand that? Well, the linearized operator tells you if you start from a small perturbation of F0 of your initial data, the linearized operator tells you how this perturbation spreads. So, I mean, since we start from some wiggles, we need this part to describe how this wiggle spread. And actually, what is interesting is that this is a dissipation. This is dissipative part, like the Boltzmann equation, it dissipates. Then the second part is more new somehow, and this is a noise which is added, or not added, but which emerges from the system. And somehow this guy doesn't dissipate, it creates some entropy. And the covariance of the process, as I said, has to be, to compute the covariance of the process, you need to understand some structure of the dynamical correlations. And this is what Herbert did, I guess even in the 80s. Okay, let me answer now Chiara's question. So the noise is white in time and white in space, but the dynamics has conserved quantities, momentum, energy due to the velocities. So the velocities have a bit more structure in order to keep these conservation laws. And this is okay. So this is the covariance of the noise tested against some function phi. Okay, so this type of things you probably recognize, and I'll come back to the entropy dissipation.
Where is the epsilon expectation?
Sorry?
Where is the epsilon expectation?
Oh, sorry, no, there's no epsilon. It's yes, thank you. Sorry, it's a limiting noise. Thank you. Sorry. So a few points I want to stress. So indeed we start from some deterministic microscopic dynamics. But the initial data are random, and what emerges in the limit due to the dynamical instabilities I mentioned earlier is that this initial randomness and this unstable structure kind of combine, and when you look at a given time on some average quantities, what pops out is a white noise in space and time. So the whole thing fluctuates, but you don't know really how, because you just looked at some averages due to this empirical, we scale empirical measure, and what you see is a white noise. By the way, it's the same noise or the same structure of noise as you would have obtained if you started from some purely stochastic dynamics as the CAX model.
Excuse me, is there a way to some intuition to understand why there is this white noise?
Yeah, yes, and maybe I'll tell you that in the next slide.
So when you say it's the same of the CATS model, so you mean that in case you find white in time and this structure in velocity?
Yes, the same velocity structure. Yes.
Okay, same velocity structure.
Yes. The proof for this model, I will not detail, but since Mitya mentioned, for example, cluster expansion, so for short time this is one of the keys, so cluster expansion to control the system. And basically, when you want a CLT in probability, well, you look at the characteristic function, here it is, and you try to compute it. Usually, should we have some probabilistic structure or some Markov chain or anything reasonable, we wouldn't go this way, because there are nice martingale structure, there are nice probabilist feature usually in the stochastic models, but here we have no stochastic process, we have nothing, so we just compute straight the characteristic function and hope for the best. Now I want to explain a few facts on another type of proof, which is for the longer time dynamics, so it's slightly different. And but before that, the longer time dynamics is at equilibrium. I want to speak about equilibrium, and that's where one understands better the structure of the noise. So equilibrium initial data is more or less product as well, except that now we want something constant in time. So namely, we assume that all the velocities are distributed according to Maxwellian and the positions are uniform. So this, once you tweak the measure by the exclusion, this measure is time invariant, microscopically time invariant, nothing happens. Again, you can define the fluctuation field. So a priori, the measure is flat. So at time, any positive time t, it's flat again. But of course, if you start from some wiggle initially, this wiggle move in time, and there's some time correlation at the level of the fluctuation, and this is what we want to look at. So it's not because we are at equilibrium that nothing happens. It's just if you zoom in at the level of fluctuation, you start from something which is going to move in time. Okay. So the second result is reads exactly the same as the first one, except that now we start from the equilibrium measure. The main difference is we don't have a short time assumption. Now we can again prove the convergence to the fluctuating Boltzmann equation, but on a longer time. I'll say a few more results about that later. And this, in this, the way somehow the noise, you don't have any choice actually. Once you know you have the linearized Boltzmann operator here, you don't have any choice in your noise. Because for physical reason, it has to satisfy what's known as the fluctuation dissipation principle. So what does it mean? Let's look now at the model at time 0. And I want to test my fluctuation field, let's say by some test function h located in this area, let's say, and some test function g located in this area. So in the limit, when epsilon goes to 0, essentially there are some delta correlation in space, and okay, one can compute what is limit. I mean, it's really simple because it's just almost a free gas. I mean, there's nothing initially, and what you want to test now is more or less the same thing, but at different times. So you at time 0 and at time t, and in the limit, one can, of course, the statement I gave before says that they converge to the solution of the fluctuating Boltzmann equation, and this fluctuating Boltzmann equation somehow decouples in time due to this dissipative structure of the linearized Boltzmann operator. However, at equilibrium, the measure is invariant. We had a microscopic measure which is invariant. So something has to compensate this dissipation, and the noise, somehow the structure of the noise is exactly built to compensate the dissipation from the linearized part.
Sorry, I didn't get it. So the noise in this equilibrium case is then different from the one in the non-equilibrium case?
No, okay. It's a good question. So it has the same, exactly the same structure. Let me show you. So it has somehow exactly the same structure. So there was a solution of the Boltzmann equation at time t, and now you have a Maxwellian. Okay? But the fact that everything is moving out of equilibrium, you don't have the same compensation. I mean, it's not that clear cut, but at equilibrium, it's it's exactly the right part to compensate. And somehow what this says is that you have a form of local equilibrium. If you imagine that your density looks like ft at time t, you can replace what should be the equilibrium by ft. But there it's a bit less neat out of equilibrium, but at equilibrium it's really the good structure. Oops, sorry. And that's why somehow it coincides with the stochastic model, because also the stochastic model has to share the same property, and somehow the limit is imposed, or the structure of the limit is imposed by this preservation, or the fact that the invariant measure has to be to remain in time. So this is a new, at least a new feature of the fluctuation, is there's some part compensating the dissipation. Another thing, okay, so this theorem is valid for a long time. At equilibrium, this convergence is valid for a long time. And if you look a bit more precisely what is the time of validity, you can even push it when epsilon goes to infinity. I can't push it that far, but you can consider some time diverging with epsilon. So okay, let me introduce a parameter alpha, and I want essentially to, and alpha is diverging, okay, very slowly. We had some discussion this morning with about mathematical physics, which was not so precise in terms of asymptotics. I mean, we have a lot of claim about asymptotics, but when it comes to evaluate at what temperature the water boils in altitude, we were not completely, depending on the height, we're not completely sure. So anyway, formally at least, this thing, even with the 3 logs, diverges with epsilon, and we want to rescale the dynamics by a factor alpha square. So there are 2 ways of doing it. One way is to increase, so before we had the 1 here in order to take into account 1 collision per unit time. So one way to increase the time is to increase the number of collisions per unit time. So here I put alpha. And we also, later on, we are also going to look at a time a bit bigger than the usual one, tau times alpha, so again, a diverging time. So what we have proved is that essentially this fluctuating Boltzmann equation remains valid on this slowly but diverging time scale with respect to epsilon. And one thing we want to do now is to look, so when time diverges with epsilon, you can reach hydrodynamic modes. So what you want to do now is, okay, let's forget about the complete structure, position, velocity. We just look at the energy and see how average over in space, how this energy spread. So for that, the energy is v square. And you time, I mean, this is the test function now, it will be v square, and you time it by some function depending on x, just to measure how energy is spreading in the system. And for the momentum, okay, now we have some function phi depending on x, and we just look at how the momentum as the test function is spreading in x. And for that, okay, so I mentioned there's a rescaling by alpha square, very indirect, but in this larger time asymptotic, the outcome of the fluctuating Boltzmann equation, it can be rescaled, and we recover somehow the Fourier-Stokes equation where the energy density somehow dissipates. And there's some additional white noise here emerging. And same for the momentum, you have a dissipation but some additional noise. So one can reach a longer time scale, at least if you consider that a triple log is a long time scale.
At this scale, you don't see the velocity anymore. The velocity has become
yes, the velocity has been averaged out
now because the structure is somehow encoded in the solution, or.
You close your eyes and you say, I just want to record the energy and see how the energy is spreading. So you integrate somehow over the velocity, and you just trying to look in terms of the position what remains.
Sorry, can you say again what are theta and u? The definition.
Okay, so this were the energy for theta and u the momentum.
So these are, I mean, psi and phi, these are two
test functions. Just to say, yeah, now I'm going to project my fluctuation field only on the energy, which is a conserved quantity, and only on the momentum, again a conserved quantity. So these two conserved quantities, what's happened is that, I mean, locally they are kind of conserved, but in time, if you rescale on a much longer time, they start to diffuse. And this is what so this is more the hydrodynamic regime, so this is what we see. And then the noise pops out here, and this is the contribution, also it's average out, but this is the contribution of the noise.
So do you really mean epsilon to infinity here?
No, I didn't, you're right, it's zero, I was over enthusiastic. Different limit, next time maybe. Thank you. Oops, sorry. Okay, so no. Yes, so now I want to go back to this theorem and for the last 5 minutes or so give you some indication on how we prove it. So the strategy there, again, we don't have good tools to handle this. So there's one part which is a kind of a tightness argument, which says the fluctuation field, for several reasons, is going to converge to something, and we want to identify this something. And this something, as Benjamin pointed out, it's a Gaussian process. So what we want to say is the following: we want to prove that the limit is necessarily Gaussian, and then compute the covariance of the limit, and at least we fully characterize the limit in this way. So the tough part there is to prove that the process is Gaussian, and again, we don't have many tools. So one way to characterize the Gaussian process is to say, I look at different times, k times, different test function for my fluctuation field at these different times, compute the product, and hope that it's going to satisfy Vic rule, because if it does, then the limiting process should be Gaussian. So we hope that this product of the k particles, or the k times, is going to split into different pairings between different times, plus some error which we want to quantify. And this, should we prove that the error goes to zero by kind of compactness, we will get that the limiting process obeys the Vic rule, and therefore the limiting process is Gaussian. And the next step is to identify the covariance of the limiting process. So the covariance of the limiting process is here. I will not detail, but it's essentially related to the transport the decay by the linearized Boltzmann operator. Actually, for short time, this covariance has been computed by Van Beijeren, Lanford, Leibovitz, Spohn in the 80s. For longer time, we had the first result with Isabelle Gallagher and Laure Saint-Raymond in dimension 2 for the covariance. And so now we have a stronger result for also the three-dimensional case. Okay, so let me summarize what the scheme of the proof. We want to compute the limiting covariance, and we want to compute or to show that the limiting process satisfies the Vic rule, and in this way characterize the process. So again, I mean, I want to do this same computation I did again and again about the covariance, so in order to understand how to compute the covariance. So let's say at time 0, I want to compute the covariance. I'm going to test with a test function h0 and test with a test function h1. So with my normalization, it's just as before, sum of n. Okay, I choose a function of mean 0 not to have to worry about it. And it's again a sum of n function here times sum of same n function. And one way to maybe to view it graphically is that the first sum in blue is a sum of n function over n points here. The second sum is a sum of n function over n points. And when I expand this thing, either I have a diagonal term as before, in which case it's a contribution which is significant, or I have two terms. Let's say here I have two somehow particles, different particles, the non-diagonal term, I is different from j, and at least initially this is 0 because the initial measure is product. So that's how we're going to do now, but we're going to do this. So there, the pairing is kind of obvious. At time 0, we can recover plenty of things, and we want to do the same thing now at different time. So the point is that now I want to test at time theta the function h1, and at time 0 the function h0. So graphically, I still have n points green here. Sorry, I mixed. I invert the color scheme. Sorry, and n points at time theta. And I want to look at the correlation when I do the expansion. But now the correlation are more complicated because there's some dynamics in between the two times. So the idea is to say, okay, this point or the function h1 at this point, I can kind of put it back at time 0, and it's going to depend on several other points. But now I'm going to rebuild a fluctuation field at time 0. So instead of having the simple somehow fluctuation field at time theta depending only on one point, I have a complicated fluctuation field due to the transport by dynamics, but at time zero. At time zero, I know everybody, and I should be able to do something. Now, the whole issue is indeed to understand this function phi k, and this k in particular is potentially very big, because there can be, over time, there can be very many interactions, and this cone is somehow representing the interaction in time. So one has to, one thing is one has to control this k, or the size and the number of particles involved in the interaction, because otherwise I can't do the same argument as before. So the strategy to control this is to proceed slowly and say, okay, I'm going to track the information at different level, split in tiny times, and each time I look how the information spreads in the system. If it spreads too much, I want to stop at this time and say that something goes wrong, and I don't want to look at it's atypical, and I don't want to look at this test function. Of course, the difficulty is stopping in the middle is not so easy, because it's still correlated with what the condition you impose at time zero, and so there the equilibrium structure is relevant. There, the time decoupling is somehow obtained only by a kind of Cauchy-Schwarz estimate to say that obtained by Cauchy-Schwarz estimate, but also behind this there's a lot of structure of the fact that we use equilibrium, we use a lot of symmetrization, we use a lot of structure in order to get averaging and in order to bound these quantities. So anyway, the strategy is in any case is the following: is trying to propagate the information backward in order to compare two things at time zero, but control how the time, because now we want to go for a long time, so control how the information spreads dynamically. When you want to do that for this case, it's getting harder and harder, because now, and I'll just conclude with that, now we have several times, time theta 3, theta 2, theta 1, and so on, and you want to propagate the information of each layer in time. And okay, so imagine now this guy has been propagated here, and now I have to look at the correlation with what's going on at the level H2. And there you see, imagine I look at the correlation between the points which are within this cone. I will get the pairing between level theta 3 and theta 2. And if not, so one of the pairing appearing here. And if I look at a different point, then we'd say, okay, the pairing did not happen, and I have to propagate it further. But all these things, I mean, keep going, and you have all these cones of the different levels, which when they start to meet, gives you you see some pairing popping out here, and if they don't, well, there's no pairing, and you ultimately you try to evaluate how this dynamical structure from each point interact, and from there you can recover the Vic-rule. Okay, so sorry, I've been a bit slow. So just to summarize, so what I presented was some results, a different type of result on the fluctuating Boltzmann equation, including more recent result in particular on the long time fluctuating Boltzmann equation and the consequence on hydrodynamic scaling. Thank you very much.
Thierry, so are there questions?
Thank you very much. I have a small question, maybe a bit technical. I mean, you showed us how do you do this stopping thing with the Cauchy-Schwarz when you do the 2 points.
Yes.
So when you have a higher order correlation, how do you do the Cauchy-Schwarz? I mean,
You do it progressively. So what counts is somehow, let's imagine you have only this guy, and then you decouple from all the rest. Once you reach this level, you follow. The whole structure. So this cone and this cone, and you decouple from what's happening behind. So somehow, in a sense, at each level here, I have only once. When I reach this level, I propagate one function which is made of this one, and I propagate it below. So, but again, it's more indeed this strategy allows us to localize some bad events in tiny areas when things can go wrong. And then we use cluster expansion actually to treat all the possible interaction between all the possible guys, and but it's okay. So one trick is actually and that is very different from BB. I mean, we use BBGKY hierarchy to go up to this level. But as such, BBGKY hierarchy is a nightmare because it's a projection. So you would see only K particles, and that is not good for us. So what we actually use is we build somehow function phi k for one interaction, but then we symmetrize them a lot. In order, and that's where the Cauchy-Schwarz is efficient because you can square and average quantities. So there is a little twist compared to just focusing on quantities just from the BBGKY hierarchy. I mean, there's also a lot of averaging behind this Cauchy-Schwarz in order to make it efficient. Should we do, just to conclude, should we do the same thing without doing the averaging? Would have, I mean, this thing without symmetrizing would be equal, but the result after the Cauchy-Schwarz would be disastrous. Other questions?
So, if I understand correctly, in this Boltzmann grad limit, right? So the number of collisions per particle at times order 1 is order 1. Right?
Yes.
Do you know something about the distribution of the number of collisions?
I think it will be relatively. I mean, you can really evaluate it at least for a short time in terms of Poisson. I guess. I mean, okay, I can't say exactly, but I would say it would have. I mean, each particle has a Poisson structure, and I think this can be. We've never done it, but this can be. I mean, evaluated at least for a short time. After to keep the control on longer time, I'm not sure, but okay. But there's no such theorem, but I think it can be evaluated. Yes.
Yeah. So if I remember correctly, originally Gallagher and Ramon and Texier, besides considering the hard sphere case, they also do the short range strong potential,
yes.
And they have the scattering maps and all this business.
Yes.
Do you think that you can have the same result if you change one for the other?
Yes, but it's much more painful. So just to give you, I mean, at least when you have, so the question is about soft potential instead of hard sphere interaction, and the strategy at the level of the proof, at least for the Boltzmann equation. So you have now particles which may interact with soft potential. So the strategy would be that's where they interact, and the strategy is more or less like that. Take a bigger ball, and then you go in like that, and then you go out, and you do as if it is a hard sphere collision, just you change your scattering. And so we would need to I mean, ultimately, so you see, this is a kind of local treatment of the, but ultimately you see the same structure as the hard sphere, except that, and when I say except, it's not a tiny thing, it's big issue technically, but you have to understand locally, I mean, how it goes, and you also have to understand events which never happen. Which would be with more, I mean, there can be more particles in this ball and so on. but I think conceptually, I mean, the same result should be valid. Yeah.
Particular also the law of large numbers, if you start close to equilibrium, holds for all times, or is it?
Okay, that's the most frustrating question, and then you'll see I have a very embarrassing answer for that. So the Boltzmann equation is like that. So you have the transport term, and then you have a collision of prime star minus, and so a collision term, okay? And there's a compensation between the two, okay? The basic Lansford strategy goes as follows. We're not able to understand the compensation, so the minus you replace with a plus, and you get some bounds like that. And there, even if you start from equilibrium and you apply Lansford's proof, you can't go beyond the time which is ridiculously small. And there's no way at the moment where we can really understand, that's something we're working on, but where we can really understand the balance between these two terms. So the strategy we use equilibrium in a very indirect way. We use equilibrium so far to simplify this interaction cone and make sure that somehow we can put it up to 2 times 0, but we never use the balance between, at least microscopically, the balance between the gain and the loss term. And of course, this is a disaster. And that's why there is no, at least to my knowledge, no simple perturbative proof. You would say, I mean, okay, Lansford is able to go up to a certain time, then if I do a tiny perturbation close to equilibrium, there's no simple proof of that, because the core of the proof is based on replacing a minus by a plus, and everything blows, and you have, even at equilibrium, you have zero control. And we don't know how to, so for the moment, okay, maybe if you give me one more second, I can give you I didn't want to mention that because it's a bit technical, but you see, equilibrium measure is of this form, and it's very useful to know that it remains in time invariant. And originally, we've been able to perturbate the equilibrium measure by an order 1, in the sense that we follow one tagged particle. So that was a level 1 perturbation. If you want to do a Boltzmann equation, even if it's a tiny perturbation, it will be by an order exponential n, because I mean, each f0, even if they are small, I mean, ultimately you have the product. So what we did, if you look at the fluctuating, when we fluctuating Boltzmann equation, as I said, we have to compute product of fluctuation fields. In terms of perturbation, we perturb by order mu epsilon k over 2. Okay, so at the moment that the furthest, at least in L infinite norm, we can go from the Boltzmann equation, but actually this is too big to play with L infinite norm. So you need already there, you need averaging, you need some understanding, but it's not so as complete as really fully understanding the balance between those two terms, which don't know how to do it.
I got one question. So I didn't understand. So in the equilibrium case, are you using the same proof that breakups earlier, or just
yes.
using a different proof?
Yeah, I mean, sorry, no, we use a different proof because somehow once you've decided that you don't go that far in time, there are different technologies which give you even much better understanding than the fluctuation. You can go up to the large deviations and so on. You can really fully understand the characteristic function. And that's the type of proof we use close to equilibrium. But no way we would be able to push it, this one. So the long time is somehow more intricate because we use different tools.
If there are no other questions, let's thank the speaker again.